Okay, brother, this is the for the question that you asked about the log of xi. Okay. So in the question actually here in your notes actually, okay, it says that recall example 2. Okay, I don't know which example they are talking about, but let me explain the thing. Okay, so it says that n is equal to 64. We have 64 random samples. Okay, we have a random sample of size of 64 from the distribution with PDF of f of x and theta. Okay, and it is equal to theta x raised to power theta minus 1. Okay, where x belongs to between 0 and 1. Okay, now here x is the sample parameter. Okay, and theta, it is the population parameter. What we do in confidence interval is that using the sample parameter we actually predict the confidence interval for the population parameter, and we say that the population parameter, for example we say that mean. Okay, so using the mean of the sample space we predict the mean of the population, and we say that okay, the mean will be in this much range. Okay, for example mean will be from 10 to 15, for example. Okay, so this is not actually an accurate estimation actually. Okay, because this is predicted via the sample mean. Okay, if we have the number of samples like high, okay, more than 50, 60, more than 100 actually, okay, then the accuracy becomes great. Okay, it is like more accurate towards estimation of the population mean or any population parameter using the sample parameter. Okay, if the sample size is small actually we have less data, and so the estimation will be less accurate. Okay, so this is the functional value. Okay, now it says that the observed samples gave the observed samples gave log of xi summation from I is equal to 1 up to 64, because we have 64 samples, so we have x value for each of the sample. Okay, for example we have mean, so the sample 1 mean is, for example we say that it is 5, sample 2 has a mean of 3, sample 3 has a mean of 4.5, and so on up to 64 samples. We need to read each of the sample. Okay, and it gives us a value of minus 18.674. okay, now this thing is actually given to us. Okay, but if you need to calculate it you must be given data. For example we have like 10 samples. Okay, 10 samples, and xi from 1 to 10, okay, it is equal to 1 2 3 4 and up to 10. Okay, it means that this is the x value, okay, and this is the I. For I is equal to 1, x1 is equal to, for example, 1. For I is equal to 2, x2 is equal to 2. For I is equal to 3, x3 is equal to, for example, 4. For I is equal to 4, x4 is equal to, for example, 5, and so on. Okay, so we can actually calculate the summation of log of xi from I is equal to 1 up to 10, because we have 10 samples over here. Okay, so we can calculate it, and it will be equal to log of x1 plus log of x2 plus log of x10. Okay, so log of x1 is equal to log of 1 actually. Okay, it will be equal to 0, log of 2, log of x2 is equal as actually log of 2 because we have x2 value of 2, so log of 2 will be equal to, for example, let me calculate it, okay, 0.3010 is the log of 2 value, okay. Now log of x3 is equal to this x3 is equal to 4, so log of 4 it is equal to 0.6020 and so on. We can find the whole values, okay. So when we make the summation of it, it will give us some value, and that value will be equal to, from I is equal to 1 up to 10 log of xi, okay. So it will give us a distinct value. Similarly, this value is actually found, okay, and this is given to us. We didn't find it, it is given to us in the question, okay. And then the theta parameter for the sample, it is equal to minus n divided by log of xi, from I is equal to 1 up to 64, okay. So and so we can n is equal to 64 and log of xi is equal to minus 18.64, so we can put it and find the estimation. This is the estimated value, okay, estimated sample value, okay, because we want to find this thing for the population, so we need to find this thing in the sample, and based on that sample value we are going to predict this theta. So theta prime or theta bar, actually this thing, it is the sample value for this theta, and this theta is the parameter, population parameter. So from this, actually what we do is we find the theta bar, actually, okay. Theta bar, it is found from sample data, and then it is used to predict the theta, which is the population parameter, okay. So the value for this theta bar is equal to minus n divided by log of xi, okay. And the standard error, it is equal to the standard deviation in theta divided by under the root n, okay. Or we can say that under the root theta square divided by n, okay. So if we have like theta value, if it is found, okay, we would put it above the, we don't need to make it square and then take under root of it, okay. We can just put it outside and take the under root of only n and divide theta bar divided by under root n, okay. This will be the standard error, okay. And the rest, you know that when it is for example, if it is two-sided, actually, okay, if you want to find like if theta is equal to up to some value and theta is not equal to up to some value, then it is a two-tailed test, okay. For that we need to z alpha by 2, okay. But if theta is equal to up to some distinct estimated value and theta is less than this estimated value, or theta is greater than, this is in one tail test. For that we need z alpha only, and we need z alpha by 2 for the two-sided, okay. Because here, if we see, for example, this is the normal distribution, okay. This is just an example, okay. So if it is two-sided, then alpha will be divided into two-sided, okay. This is why we find the z alpha by 2. So if it is, for example, one-sided, actually, so it is undivided, so we call z alpha. And if we want to do the left side test, actually this one, we call minus z alpha, okay. and this is positive z alpha, which is the right side, and this is left side, and this is two-sided ts. Okay, so that is how the whole situation actually works. Okay, I hope you find it useful and you understand it now. Okay, and as we want to find, like, confidence interval. Okay, so for confidence interval we also need two-sided. So okay, we need two sides, the lower range and the upper range. Okay, so it means that we will calculate c alpha by 2. Okay, so that is for the example that you were confused about. Okay, thank you. Okay, so in this video what we will do is we will explain how chi-square distribution actually approaches normal population or is equal to normal population for higher sample sizes, like n greater than 30. Okay, so let me graph it. Okay, so if we graph the chi-square distribution, okay, for the relative degree of freedom, actually what we get is we get this shape when the degree of freedom is like 2 or 3. Okay, and if degree of freedom is actually, for example, 5, if df is equal to 5, then we get, then this bump it reduces and the length actually elongates actually. So we get actually somewhat this kind of shape. Okay, now if degree of freedom is greater than, for example, 10, what we get is we get this kind of bump. Okay, and if degree of freedom is becomes more and more, we see that this actually, the lattice that we draw, it is approximately equal to the normal distribution. Okay, how we deal with normal distribution is we have like a bell-shaped curve similar to this thing. Okay, so if we see this thing, it is approximately equal to this thing. Okay, this is for normal and this is for chi-squared. So when the degree of freedom actually increases, the chi-square distribution approaches to normal distribution. It is equivalent to the normal distribution. That is why we can use it interchangeably for the large sample. So if you are given that we have a large sample, for example 90 size or 80 size or 75 size, okay, we have a large sample, okay, and it follows chi distribution, so we can easily do it with the normal distribution and vice versa. Okay, we can use both to solve depending on the situation. Okay, so if you want to find the confidence interval for variance of a population, okay, this is a variance of a population. Okay, so if you want to find the confidence interval for variance of a population and the sample size is large, by large I mean that greater than 30. Okay, so if this situation is here, we can actually use two formulas. Okay, the first thing is that we are actually, it is explained in the book. Okay, okay, this is chi-square left. Okay, the chi-square left, and it is equal to chi-square right. Okay, and it is equal to chi-square right, it is equal to 1 minus alpha, okay, and this is the degree of L1 alpha and the degree of freedom, which is V, and V is equal to n minus 1. Okay, degree of freedom is equal to V and V is equal to n minus 1. Okay, similarly the chi-square left is equal to chi-square alpha and V. Okay, and V is equal to degree of freedom and it is equal to n minus 1, and alpha is the level of significance. Okay, this is given to us. Okay, so this is how you can find it. This is the standard way of doing it. Okay, this is the standard way of doing it. Okay, now your professor actually he has come up with the solution with another formula. Okay, and that is equal to, because what we say that for the theta or the sigma square confidence interval, we say that the estimated value of sigma square plus minus z of alpha by 2, because it is two-sided, so we can say that alpha by 2. If it were only one-sided, okay, because confidence interval is two-sided, we need the range for two sides, the left and right, so we can say alpha by 2, okay, into the standard error for sigma square. Okay, so this thing actually he has evolved a formula and it is equal to 2 into estimated value of sigma square whole square divided by n. Okay, or sigma square value into under the root 2 divided by n. Both can be used interchangeably, but you should use this one. Okay, it will be a confusing. Okay, so if you use this one and use z instead of the chi-square, we can use this formula. Okay, so confidence interval for sigma square, it is equal to the estimated value of sigma square plus minus z alpha by 2, okay, into under the root 2 estimated value sigma square whole square divided by n. This is the another formula that can be used interchangeably. Okay, if we are not using the chi-square values, so you can use both. You can use either chi-square or you can use other z. Okay, but for the z actually the chi-square will give you a confidence interval which has the short width. Okay, but in z this one the width will be a bit long. Okay, the range of the value in z will be a bit long, and in the x, the x square or chi-square or chi-square, whatever you call it, okay, this width is low. The width is, for example, here you can find the values from 9 to 12, and in the z case you can find the values from like 8 to 14 maybe. So the width here is higher, the width here is lower. Okay, that is the difference. I hope you have understood this thing also. Okay, and also the approximation of chi-square or chi-square distribution with the normal distribution as the degree of freedom or the sample size increases. Okay, so as we increase the sample size, okay, so the degree of freedom will also increase, because degree of freedom is equal to n minus 1, sample size minus 1. So as we move towards the higher degree of freedom or higher sample size, the chi-square distribution actually approaches the normal distribution, which is equal, we can alternatively say that the chi-square distribution is approximately equal to the normal distribution for n greater than or equal to 80 or 90, the large samples. So you can use both of them interchangeably. Okay, this is when we use z distribution, and this is when we use the chi-square distribution or chi-square distribution. Okay, that is the main difference. Okay, so whatever you use, if you use the z formula or the z value, or you use the x square or the chi-square value, depends on you. You can use both interchangeably. Okay, but this one is the standard way to do it. Okay, and this one is, kind of made up formula. Okay, but in the notes this was mentioned, so that is why I explained this also. Okay, otherwise you go for this formula. In majority of cases, we will be given n and s, and we can use this formula to calculate the confidence interval of the variance of the population. Thank you. Okay, in this video we will try to compare the variance confidence interval when we find it using the chi-square values and when we find it using the z value. Okay, so and we will use the same question, okay, that is in the notes. So confidence interval for the sigma square or variance. Okay, sigma square is variance. Okay, but variance of population actually. Okay, not of the sample. The sample is the estimated value, which is with a cap actually. Okay, this thing is for the sample. Okay, so first attempt we're using the chi-square value. Okay, values. Okay, we know that actually the okay, now this chi-square right actually, or chi-square 1 minus alpha and degree of freedom. Okay, and chi-square left actually, it is equal to chi-square alpha and degree of freedom. Now we have in the question, we have n is equal to 81, implies that the degree of freedom is 81 minus 1 is equal to 80. We have a large sample size, quite large sample size. Okay, so putting the values, and s square is equal to 11.738. Okay, this is given. Okay, n is given, and the population standard deviation or population variance is also given. Okay, these two things are given to us. So now putting these values, in, for example, we say that this is equation A. Okay, in A what we get is 81 minus 1 into 11.738 divided by chi square for 1 minus alpha and degree of freedom is 80. Okay, 81 minus 1 is 80. Um, 81 minus 1, the numerator will be same actually, divided by only the denominator value will be changed. Okay, alpha and 80. Now alpha is equal to 0. For example 0. Here I guess, let me see what is the value of alpha. I guess it is 0.1. We want to find 90% confidence interval. Okay, the confidence interval is 99%. Okay, so alpha is equal to 0.01. Okay, because we want to find the 99% confidence interval. Okay, so alpha is equal to 0.01. so let's continue it. Putting alpha is equal to 0.01. Okay, so we have 80 into 11.738 divided by 80 into 11.738 divided by this value and this value. Okay, now we need to find chi square of 1 minus alpha is 1 minus 0.01 and 80. This is to be found, and chi-square of 0.01 and 80, this is to be found. Okay, this will give us 0.99. Okay, so chi-square of 0.99 and 80, and chi-square of 0.01 and 80, these two values. Okay, let me first tell you a bit of the chi-square distribution. Okay, we know that the chi-square distribution is actually skewed. Okay, it is not symmetric, so it means that it is not equal on both sides. Okay, so this is something like this. Okay, it means that it is not symmetrical. If the mean is on this region, you know that this area is large and this area is smaller, so it will be positive symmetric. This tail will be higher than this region. Okay, this is the quality, one of the characteristics of the chi-square distribution. Okay, because it is positive skewed. Okay, if this region was greater, it would have been the negative skewed. Okay, like this one. Okay, now this one is negatively skewed. Okay, this area is larger and this tail region is smaller. Okay, here the tail region is actually larger and this region is smaller, so it is positively skewed. This is negatively skewed. Okay, so in this one, this is the critical region. Okay, or the area of rejection. Okay, and this is the chi-square value for actually 1 minus alpha and 80, because this is the area of acceptance. Okay, and in this one, this is the left one, and this is the area of acceptance for this. Okay, so let's find out these two values and put it in the equation. Okay, so 1 minus alpha or 0.99, it is equivalent to this 0.01. Okay, in the right tail one. Okay, so let me zoom in. Okay, so 0.01 and the degree of freedom should be 80. Okay, so this is the right to the right of the critical value. This is the range of values to the right. So here it is equal to 112.329. Okay, 112.329. Okay, now doing this one. Okay, 0.01, so it means that we have to find in the right one a 0.99 and 80. Okay, so let me show you the how to do it. Okay, this is 0.99 and against 80 we have a value of 53.540. 53.540. Now putting the values in the equation. Okay, so the numerator actually, it will get us a value of the first numerator 939.04. Okay, divided by this one 112.329 less than sigma square, and sigma square is less than 939.04 divided by 53.540. So let's calculate it and see what range for confidence interval do we get. Okay, 939.04 divided by 112.329, we get 8.359, so 8.36. Okay, 8.36 less than sigma square, and sigma square is less than Now let's get to the second part. 939.04 divided by 53.540. We get 17.54. 17.54. Okay, so the 99% confidence interval for sigma square is equal to 8.36 and 17.54. So we are 99% sure that this is 99% probability that the variance of the population will lie between 8.36 and 17.54. Okay, this is our estimation based on the chi-square formula. Okay, now let's compare it with the z formula. Okay, now this is already solved, so I will use that one. Okay, so it gives us a value of, when we use the z formula or the z statistics, it gives us a value of 6.988 and 16.488. Okay, 6.9 and 16.4. So let's write it. Based on z, we get 99% confidence interval for sigma square is equal to 6.98 and 16.48. Now see, this one has, what we say, the range. This one is a bit slick actually, and here the range is, it is a bit vast. Okay, so it is more accurate. Okay, because we have large data. This one is more accurate than this one. Okay, but both can be used interchangeably. Okay, we can use both. Okay, the textbooks prefer this thing that I am actually here, what you sent me, that textbook actually. And we also read about this thing when I was doing graduation. But the professor's formula is using the z statistics, and this gives us this range. Both are kind of pretty close if we analyze it. Okay, both are pretty close. So now it's upon you which one do you want to use. Okay, but read the question carefully in the exam, and you can then come up with a solution like which one to use. Okay, so in this video we will do the question number 20, which is on page number 333. Okay, page number 333. Okay, so the question says that a district official intends to use the mean of a random sample of 156 graders. Okay, so 6th grade students, okay, a total of 150 are being studied, so n is equal to 150 over here. Okay, from a very large school district to estimate the mean score. Okay, what we want to estimate is, we want to estimate the mean score that all the 6th graders in the district would get if they took a certain arithmetic achievement test. Okay, so they want to hypothesize actually the mean score. Okay, so if based on experience the official knows that standard deviation sigma, okay, it is equal to 9.4. okay, so this is the, whenever sigma is given, this is the population standard deviation. Okay, this is not the sample standard deviation, this is the population standard deviation. Okay, it is equal to 9.4. okay, for such data, what can she assert with probability p is equal to 0.95 about the maximum error? Okay, so what we want to find is, we want to find the error. Okay, so we will use the formula of the confidence interval over here. Okay, so confidence interval for mean is x bar plus minus z alpha by 2 into standard deviation divided by under the root n. Okay, so we know that confidence interval is equal to the sample mean plus minus margin of error or error. Okay, so we need to find this part only. Okay, we are interested in this part only. Okay, so this part contains error is equal to z of alpha by 2 multiplied by standard deviation of population divided by under root n. So alpha is equal to 1 minus p is equal to 1 minus 0.95, so it comes 0.05. So z of 0.05 divided by 2 multiplied by standard deviation is 9.4. Okay, so 9.4 divided by under root 150. So this will give us z of 0.025, it is equal to 1.96. Okay, so 1.96 multiplied by 9.4 divided by under the root 150. So the error that we get over here is equal to 1.50. Okay, this is the error of the score that a student, a sixth grader can get. Okay, and this is under root 150, it gives us 12.25 approximately. Okay, and just doing the calculation we will get 1.50, which is the required result. Okay, so this is how this question should be done. Okay, now moving to the question number 21. Okay, so question number 21 says that with reference to this question number 20, actually using this data, okay, suppose that the district official takes her sample and gets x bar is equal to 61.8. Okay, so now x bar is equal to 61.8, which is the average or mean score, average score of sample. Okay, so use all the given information to construct a 99% confidence interval. So 99% confidence interval is to be found. Okay, so solving this, actually we have x bar is equal to 61.8, standard deviation of the population is 9.4. Okay, so when standard deviation of the population is known, actually then we can use the z statistics. Okay, so the 99% confidence interval, it will be equal to x bar plus minus z of alpha by 2 into standard deviation divided by under the root n. But now here it is 99%. Okay, in the upper one actually it was 95%. Okay, so alpha was 0.05. Here alpha is equal to 0.01, and we can find it by 1 minus p, and 1 minus 0.99, it gives us 0.01. So z of alpha by 2 is equal to z of 0.01 divided by 2, which is equal to z of 0.005. Okay, and it gives us a value of 2.575. Okay, this is the value that we get from z of 0.005. Okay, so now the 99% confidence interval for mean mu, it is equal to x bar plus minus z of alpha by 2 into standard deviation divided by under the root n. So x bar is known to us, which is 61.8 plus minus z of alpha by 2, which is 2.575 multiplied by standard deviation, which is 9.4 divided by under the root 150. Okay, so calculating this, it will give us a value of 61.8 plus minus 1.98. Okay, this is the 99% confidence interval for mean mu. Okay, so it will be equal to 61.8 minus 1.98 and 61.8 plus 1.98. Okay, so it will give us 59.82 and 63.78. Okay, so the mean of the population mu, it lies between 59.82 and 63.78. So the 6th graders actually will score an average of, this between this 59.82 and 63.78. This will be the average score for the population of these 6th graders. Okay, so this is question number 20 and 21 being solved. Now I am sending you some other problems also. Okay, this is question number 24 on page number 333. Okay, and it says that a study of the annual growth of a certain cacti showed that 64 of them selected at random in a desert region. Okay, the investigator is actually investigating cactus plant, and 64 of them are selected as a sample. So the sample size is equal to 64. Okay, selected at random in a certain desert. Okay, grew on an average of 52.80 mm. Okay, so this sample actually, it shows an average. This is the sample average x bar. Okay, it is equal to 52.80 mm. Okay, this is the length of the plant on average from this sample 64 sample studied. Okay, with a standard deviation of 4.5 mm. So the sample standard deviation is 4.5 mm. Okay, it says that construct a 99%. So 99% confidence interval for the true average mean for the mu. Okay, 99% confidence interval for the mu. Okay, so solving it, we have n is equal to 64, which means that it is large sample. Okay, and we have x bar and s. We don't have the standard deviation of the population is unknown. Okay, but still the population size, the sample size is larger, it's greater than 30. So we will use the z statistics over here. Okay, so 99 for 99% ci alpha is equal to 1 minus 0.99, which is equal to 0.01. Okay, now 99% confidence interval for mean is equal to x bar plus minus z of alpha by 2 standard deviation divided by n. This will be replaced by s. Okay, so we can write it as x bar plus minus z of alpha by 2 into s divided by under the root n. Okay, now we have this thing. we have this and we have this. So putting the values, okay. So x bar is 52.80 plus minus z of alpha by 2. So z of alpha by 2 will be equal to the z value for 0.01 by 2, which makes it 0.00 and 5. Okay, z of 0.005 into s value is 4.5 and under the root n is 64. Okay, so solving it, actually z of 0.05, it will give us a value of 2.575 multiplied by 4.5 divided by under the root 64 would be equal to 8 square is equal to 64. So solving this, we get 52.80 plus minus, and this will give us 1.45. okay, so 52.80 minus 1.45 comma 52.80 plus 1.45. This is the range. So 51.30 comma, and it will give us 54.05. So this is the 99% confidence interval for the mean of true population. Okay, true population mean, it means that the cactus plant, actually it will grow an average height of somewhere between 51.30 and 54.05 mm. okay, and we are 99% confident. okay, probability is that it is true by 99%. okay, so this is how this question was solved. And question number, actually the question number 22 and 23 are actually same as question number 20 and 21. okay, so now we have done like 5 problems. okay, now question number 28. okay, this is a bit tricky, so you have to focus on this one. okay. It says that an efficiency expert wants to determine the average amount of time it takes a pit crew to change a set of 4 tires on a race car. okay, use the formula for n to determine the sample size that is needed. okay, so we need to determine the sample size n. okay, so that the efficiency expert can assert with probability of 0.95 or 95% that the sample mean will differ from the population mean mu, the quantity to be estimated, okay, that is mu, by less than 2.5 seconds. okay, it means that the difference between x bar and mu, it is equal to 2.5 seconds. okay, while x bar is the sample mean of changing tires on race car, and mu is the population mean that we want to find, actually. okay, population mean to change tires on race car. okay, and the difference between this population mean and the sample mean is 2.5 seconds. okay, so they want us to find actually the sample size n, okay, for which the investigator can can say that we are 95% probable actually that these two are differed from each other by 2.5 seconds. okay, so we can use like two formulas over here, okay, and it is known as from the previous studies that sigma, the standard deviation of the population, is equal to 12.2 seconds. Okay, so sigma is known. Okay, sigma is known, it means that we have to use the z statistics. Okay, so we know that z is actually equal to x bar minus mu divided by standard deviation of population divided by under the root n. Okay, this is a basic formula that you should know. Okay, z is equal to x bar minus mu divided by standard deviation divided by under the root n. So in order to find n, what we do is we can write it as z is equal to x bar minus mu multiplied by under the root n divided by standard deviation. Okay, this is, we use the rule of a divided by b divided by c, which is equal to ac divided by b. Okay, this rule is followed here. This is equal to a divided by b divided by c, so a multiplied by c divided by b. Okay, so z is equal to x bar minus mu into under the root n divided by sigma. Okay, now what we do is we will find the value of n, the sample size. We need to find the sample size. Okay, alpha over here is equal to 1 minus 0.95 because the probability given is equal to 95%. Okay, so alpha is equal to 0.05. Okay, so z is equal to x bar minus mu multiplied by under the root n divided by standard deviation. Okay, so z multiplied by standard deviation is equal to x bar minus mu into under the root n. Okay, so here we have multiplication, so when it moves to this direction, so we find that under the root n is equal to z multiplied by standard deviation divided by x bar minus mu. Okay, and n is equal to, or we can say that under the root n whole square is equal to, taking squares on both sides. Okay, taking square on both sides. Okay, so we get z multiplied by standard deviation divided by x bar minus mu whole square. Okay, so this square root and square, they will cancel each other out, and we get n is equal to z into standard deviation divided by x bar minus mu whole square. Okay, now here actually we have the following values. We have standard deviation, we have x bar minus mu. We know that x bar minus mu is equal to 2.5 seconds. Okay, this is given to us, so putting all the values actually, okay, now this z is equal to z of alpha by 2. Okay, this z is equal to z of alpha by 2, so z of 0.05 divided by 2 is equal to z of 0.025. Okay, and this is equal to 1.96. Okay, so n is equal to 1.96 multiplied by standard deviation. Okay, standard deviation is equal to 12.2 seconds. Okay, divided by x bar minus mu is equal to 2.5 seconds and whole square. So taking the whole square, we get n is equal to 91.48. Okay, so it can be rounded off to 92. So the sample size is 92, for which we can assert that there is a 95% chance that the difference between the sample mean and the population mean is 2.5 seconds. Okay, thank you. Okay, so you were confused about this thing that we use the ratio of the population variances. Actually, when we used to find the ratio of the population variances, we use the ratio of the sample variances S1 square divided by S2 square. Okay, this is same like we use the population mean. Okay, we use the population mean x bar to find range of the sample mean. We use the sample mean x bar to find the range of population mean mu. Okay, how we do it? We do it using the z statistics. Okay, we know that z is equal to x bar minus mu divided by standard deviation divided by under root n. Okay, so we use this statistic to find this mu. Okay, so from this mu is equal to z, because it is two-sided. Okay, the range is two-sided, the lower side and the upper side. Lower range UCL and LCL. Okay, LCL and UCL, lower control limit and upper control limit. Okay, so u is equal to z into standard deviation divided by under the root n and plus minus x bar. When we rearrange it, we can say that mu is equal to x bar plus minus z into standard deviation divided by under the root n, which is exactly the same formula actually that we use for confidence interval definition. Okay, this is the margin of error and this is the sample mean. Okay, so the population mean mu, it is equal to sample mean plus minus the error that it can get, the total number of the error, the total error that it can actually deviate. Because we have sample data is less, that is why there is always a chance to make some errors. So what we do, we plus and minus that error from the sample mean, and we say that the population mean will lie somewhat between this range. Okay, similarly what we do in sigma 1 square divided by sigma 2 square, which is the ratio of the population variance, we used to predict or find this ratio using the ratio of the sample variances. Okay, and how we do it? We do it by this formula. Okay, s1 square divided by s2 square multiply by f of 1 minus alpha by 2. Okay, and 2 minus 1 and n1 minus 1 comma f of alpha by 2 and 2 minus 1 and n1 minus 1. Okay, but the only thing that is difficult in this thing is that this value we can find the alpha by 2 and 2 minus 1 and 1 minus 1. Okay, this is the degree of freedom for the numerator and this is degree of freedom for the denominator. Okay, in this case. Okay, we can this can be seen in the table, but this value f of 1 minus alpha by 2 and 2 minus 1 and 1 minus 1, this cannot be traced in the can't be traced in table. In the critical f values in the table, you will not find this value. You have to use the internet resources or anything like that, but you will not find it in table. So to make it uniform and to make it possible to find it in the table, what we do is we use the ratio, okay, and we multiply it with 1 divided by f of alpha by 2 and 1 minus 1 and 2 minus 1, okay, and f of alpha by 2 and 2 minus 1 and 1 minus 1. This will remain the same, okay, this remain the same, only this thing changed, okay. And we know that f of 1 minus alpha by 2 and 2 minus 1 and 1 minus 1, it is equal to 1 divided by f of alpha by 2 and 1 minus 1 and 2 minus 1, okay. So that is why we put this instead of this. Now this value, this thing, it can be found in the table, okay. So just dividing it by, dividing 1 by this value and multiplying by this, you will find the lower range, okay. S1 square divided by S2 square into 1 divided by f of alpha by 2 and 1 minus 1 and 2 minus 1, okay. This will give us lower range, okay, lower range value. And S1 square divided by S2 square into f of alpha by 2 and 2 minus 1 and 1 minus 1, this will give us the upper range, okay. So that is how it is done, okay. This is simple, this is not that difficult. Don't confuse yourself with 1 minus alpha by 2 and all that, okay. You need to focus on this thing. This in the first one we have alpha by 2 but and 1 minus 1 and then 2 minus 1. In the second one we have alpha by 2 but and 2 minus 1 and 1 minus 1, okay. So if the number of samples for sample 1, population 1 and population 2, actually if the number of samples taken from population 1 and population 2 are same, then you will get the same values. But if it is different, you will get a different value, okay. I will make an example of it, and I will do it here, okay. So n1 in the example 11, okay, I am doing example 11 and it is on the page number 331, okay, page number 331, okay, 331, example 11, okay. I will use this formula. So n1, the sample size of 1 is 10 and 2 is equal to 8. S1 standard deviation is equal to 0.5 and standard deviation 2 is equal to 0.7, okay. So we need to make it variance, okay. To convert the standard deviation into variance, we square it, okay. So 2.5, you will get this, and S2 square is equal to 0.7 square is equal to 0.49, okay. Now we have found it, we need to find the ratio of it, okay. S1 square divided by S2 square, we get 0.25 divided by 0.49, okay, and we get 0.510 or something like that, okay. Now what we need to do is we need to multiply 0.510 with 1 divided by f of alpha by 2 and 1 minus 1 and 2 minus 1, and also with f of alpha by 2 and 2 minus 1 and 1 minus 1, okay. So this thing, first doing this thing, okay, f of alpha by 2, alpha here is equal to 0.02 because we want to find 98% of confidence interval. So 1 minus p is equal to alpha, 1 minus 0.98 is equal to 0.02, okay, and alpha by 2 will become 0.01, okay, and 1 minus 1, and 1 is equal to 10, 10 minus 1 is equal to 9, and then 2 minus 1 is 8 minus 1, which is become 7. So look this value in table and now this one. So the alpha by 2 will remain same. Now n2 minus 1 is equal to 7 and n1 minus 1 is equal to 9. So I need to look these two values and I will get it on the same spot, okay, in the table. So let's look at the table, okay. So now this is the f critical values, okay. This is the degree of the numerator, which is up to 9, and this is the degree of the denominator, which is up to 7, okay. Now the first value is f of 0.0197, okay. It means that the numerator is 9 and denominator is 7, okay. So the numerator is 9 and denominator is 7, okay. So I need to look it in front of 7 and below the 9, but the probability is 0.010, this one, 0.01 alpha by 2, okay. So let's look at, I will get over here is 6.72, okay. So the first value I get is 6.72. So I can write here 6.72. Now need to look f of 0.01 and 79. The numerator is now 7 and denominator is 9, okay. So now the numerator is 7 and denominator is 9, okay. So going to the next page, okay. This is 7 and this is 9, and I need to find 0.01, okay. So it is giving me a value of 5.61, okay. Writing it 5.61. Now putting the respective values, okay, what we get is 0.510 multiplied by 1 divided by 6.72 and also 5.61. So when we do it actually separately, we get 0.510 multiplied by 1 divided by 6.72. This will become the lower range, and comma 0.510 multiplied by 5.61, this will become the upper range, okay. So let's, when we calculate it, actually we get the lower range is 0.076, okay, and the upper range that we get is 2.862, okay. And this is the ratios for the variance of the population. It means that the population ratio, the population variance ratio, okay, it will lie somewhere between 0.076 and 2.862. This is the range, okay. So that is how it is found, okay. We will do now exercise question number 17, which is on page number 331, okay. This is the page number, okay. It says that if it can be assumed that the binomial parameter theta assumes a value close to 0, upper confidence limit of the form theta less than equal to c are often useful, okay. Find a random sample of size n. For a random sample of size n, one-sided interval is the one-sided interval, it is given by this formula, okay. This formula is given to us, chi square of alpha and 2 into x plus 1, okay. This is the one side actually interval, okay. Confidence interval, one side, because we have two sides in confidence interval, okay. This is for the theta is less than, okay. So we have confidence interval like theta is greater than, okay, and theta is less than, okay. These two are the values. So this, the right hand side value, the upper range UCL is denoted by this formula, okay. This is the upper limit, upper control limit, okay. So because theta is less than that, okay, and theta is greater than this value and less than this value, so this is the upper range, okay. Now it says that use this formula to find 99% confidence interval, okay. Use this formula to find 99% confidence interval. It means that alpha over here is equal to 0.01. Okay, here we have alpha, so for alpha we will put 0.01. Okay, and the other information that it gives us is that for the proportion of defectives produced by a process if a sample of 200 units, okay, so n is equal to 200 units contains 3 defectives, so x is equal to 3. We know that the theta is equal to x divided by n. Okay, number of defectives over total sample size. Okay, so x over here is 3 and n is equal to 200, and the upper limit is denoted by this. So let's put all these information into this equation. So we get 1 divided by 2 into 200 multiplied by chi-square value of 0.01 comma 2 into x is 3. Okay, so we get is 1 over 400 multiplied by chi-square value of 0.01, and 2 into 3 plus 1 is 2 into 4, which is equal to 8. So let's find this value, chi-square value, from the table. Okay, so what we get is 1 over 400 into this value. Let's define this value. Okay, so the value for chi-square 0.01. Okay, and degree of freedom is 8. Okay, so 8 again 0.01, we get 20.090. Okay, so I will put this value. Okay, 20.090. Okay, so when we divide 20 by 400, we get the value of 0.050. Okay, this is the upper control limit, okay, for the confidence interval hence found. Okay, this is question number 29. Okay, this is a problem which is kind of tricky, so we will do this. Okay, so the problem says that in a study of television viewing habits, it is desired to estimate the average number of hours that teenagers spend watching per week. If it is reasonable to assume that sigma is equal to 3.2 hours, okay, the population variance is equal to 3.2 hours, and it is given. Okay, how large a sample is needed? N is to be found. Okay, is needed so that it will be possible to assert with 95% confidence. Okay, it means that alpha is equal to 0.05. Okay, that the sample mean is off by less than 20 minutes. Okay, it means that x bar minus mu, it is equal to 20 minutes, which is equal to 1 over 3 hours. Because we have standard deviation in hours, so we converted these minutes into hours. Okay, now we know that z is equal to x bar minus mu divided by standard deviation divided by under the root n. Okay, so z and alpha value is 0.05. Okay, so z of alpha by 2, because it is two-sided. Okay, which is equal to z of 0.025. Okay, so z 0.025 multiplied by standard deviation divided by under the root n is equal to x bar minus mu. This x bar minus mu is equal to 20 minutes. Okay, and it is equal to 1 over 3 hours. Okay, either convert these minutes into hours or either convert these hours into minutes, you will get the same result. Okay, so you can do both. So z value of 0.025, this is 1.96, multiplied by standard deviation is 3.2 divided by under the root n is equal to 1 over 3. Okay, this is division over here. When it will move this side, you will get 1.96 multiplied by 3.2 is equal to 1 divided by 3 multiplied by under the root n. Okay, so here 3 is in division. Okay, it is 1 by 3 is in multiplication, so 1.96 multiplied by 3 by 2 divided by 1 by 3, okay, is equal to under the root n. When we square both sides, okay, we get n is equal to 1.96 multiplied by 3.2 divided by 1 by 3 whole square. Okay, so what we can do is we can multiply these. Okay, 1.96 multiplied by 3.2, we will get about 6 point something. Okay, multiply by 3, 1 over 3, we will reuse the rule a divided by b divided by c is equal to ac divided by b. So 3 will move upward. Okay, and we can square it to find the value. Okay, or we can do this like this. Okay, so these two will give us 6.272 whole square divided by 1 over 3 whole square. Okay, so we will get this whole square, we will get 39.33 divided by 1 by 9. Okay, so 39.33 multiplied by 9 is equal to 354. So n is equal to 354. Sample size is 354. Okay, this is question number 29.